Question 3 from the 2013 Level 2 mechanics paper. Each bumper has a rubber bumper all around it, bumper car. This is momentum and energy. The mass of a bumper car is 240 kilograms, 2SF by the look of it there. Jason has a mass of 65 kilograms, which means 305 kilograms for this, and travelling at a speed of 2.4 metres per second. Calculate the size of the momentum of Jason in his bumper car. Momentum is mass times velocity. So you need to have the mass, which is the 240 kilograms plus the 65 kilograms, and you multiply that by the 2.4 metres per second squared. Whatever that gets you is whatever it is. The unit's going to be kilogram metres per second. That's kg, which is the mass part, times the velocity part, ms to the minus 1. B. The bumper car is designed to minimise injury. Discuss the reasons for the bumper cars having rubber bumpers all around them. Assume cars with and without bumpers have the same mass. Assume change of velocity is the same with and without bumpers. Okay, if you're familiar with past exams, you'll know exactly what this question is getting at, and you will be able to answer it very quickly. It's getting at the momentum and impulse kind of aspects. I'm getting myself mixed up there. The change in momentum is the force times the change in time. So when both the cars have the same mass and change in velocity is the same, we're talking about momentum mass times velocity change gives us the same change in momentum. So we would start it off for the same change in momentum. You have a bumper car with a rubber bumper, and the bumper would increase the amount of time that it takes for the impact, for the collision to take place, for that momentum to change. If you have an increased time, that means you're going to have a decreased instantaneous force if you have the rubber bumper, which means you would have less injury for the one that experiences lower overall forces. Same change of momentum. One of them have a longer time of impact, which sounds a little bit counterintuitive. If you're taking part in a collision that takes longer, you'd think there's more chance of having impact, but if it takes longer for the same change of momentum, you'll have lesser overall forces, and therefore you will have lesser injuries. Anyway, we'll move on. C. Jason collides head-on with Janet, who is in another bumper car. The bumpers don't work properly, and after collision they lock together. The mass of each bumper car is 240 kilograms. Jason has mass of 65 kilograms, Janet has mass of 58 kilograms. They're travelling towards each other in opposite directions. Jason with a speed 2.4 metres per second to the right, Janet with a speed 2.7 metres per second to the left. Getting a little bit complex. You've got to do it very carefully when it gets complex. Calculate the combined velocity after the collision. Include a direction with your answer. So there's going to be conservation of momentum. So that means the total momentum before must equal the momentum after. For that, that's easy. Then we've got the mass times velocity for Jason. There we go, JAS. And then we've got to add the mass times velocity for Janet. Remember though, the velocity of Janet, if you take Jason to be in the positive direction, that means Janet will be in the negative direction. So you're effectively subtracting Janet's momentum from Jason's. Whatever your final answer, if it's positive, will mean that the final direction is going to be to that way, if it's positive, because that was the direction we took for positive initially. If the direction is in the other direction, Janet's direction, it would be negative. So you've just got to do that calculation and find out who has the greater initial momentum, and add them together. That'll get the magnitude. So your momentum after, to find the actual speed, because plus or minus will determine the direction, but to find the actual speed, you're going to have to do that momentum afterwards divided by, that's a percentage point, divided by the total combined mass, which is going to be 240 plus 240 plus 65 plus 58. So you have to include the total mass for the total of everyone. and whatever you get, units will be metres per second, two significant figures for your final answer. D, now this is where it gets a little bit interesting. Part 2 of D, there was a lot of controversy on the physics teachers forums about how to answer the question. So I'm possibly going to address some of that, otherwise if I don't, at least you can have a bit of confidence if you weren't sure quite how to do it. That confidence that you weren't necessarily having an issue with your own physics understanding. Anyway, moving on. The rubber bumper in Jason's car has a ginormous spring constant, 78,000 newtons per metre. On one occasion, he collides with the wall, causing a compression of 15 centimetres. Calculate the elastic potential energy stored in the rubber bumper. Now, we've got a formula for that. Elastic potential energy equals half kx squared. So we're told the spring constant k, so that's no problem, we've got that. We know the extension. The only trick there is we have to make it in metres, 0.15 metres, which a lot of people don't do, and don't forget to square it. And whatever you get will be the energy stored, units of joules. Okay. Part 2 anyway, determine the impulse. The impulse. If the collision lasted for 0.80 seconds, include a unit with your answer. Okay, so we clearly have the time of the collision. 0.80 seconds, so that's fine. So it seems that our quest is to find what this force will be. We've got the impulse, the change of momentum, and the impulse force. But we need that force. We have a few issues though. You might think it's as simple as just doing F equals kx, but that would be wrong. You can't do that. The reason you can't do that is the force is not constant at that value to produce that extension of 15 centimetres or compression of 15 centimetres. So what you would actually have is for the extension or compression, you would have a varying force. Now, what's nice about this is, if this is correct, you should be able to just take the maximum force and divide it by 2 to get the average force. That's the force at 15 centimetres. So if you were to do that, you would do F equals kx, being 78,000 times by 0.15, and that will give you a force, and then you divide that force by 2. The other way you could look at it, actually that should be fine, is, and this is where it got really tricky, is using simple harmonic motion, which you won't learn about year 12s or level 2 physics students until year 13, it's level 3, and saw a really elegant solution for this using simple harmonic motion. It was very cool. And what it showed, if I'm remembering correctly, it was some months when I looked at it and we had this discussion. But if we consider that I totally forgot what I was going to say. No, it turns out that the question is over, what we'd call over-constrained. That means it's given too much information. I think that we find that the collision did not last for this particular time if we use the simple harmonic motion method. Unfortunately, sometimes these papers have problems and they're not as well written as they could be. Everybody makes mistakes, so that's, it's not really something we can get too up in arms about. We would hope that there's a clear process for looking at these questions to make sure that they're doable and that they're fair. In this case, I think this is fair enough, that if you can find the average force using your understanding here. Oh, that was the other one. You could use the... No, I'm not going to get into that. It's already too long. So I think it's fair enough that you could do it, but with the space given to you, you would expect that this is a relatively simple question, so you'd think you would just use this and plug it in. But maybe you could get achieved if you use this, and merit if you used the average force, and a super duper excellence if you use the simple harmonic motion method to get it. But check out the marking schedule for a little bit more detail. That's all I have to say.